Hello everyone, and welcome to this example recording on analysis by inspection with current sources. So in this example, we're going to be using analysis by inspection to determine the voltages V1, V2, and the voltage V3. Right, so the first thing that we then need to do is to use our Ohm's law expression to determine the final equation or matrix configuration for the output that we're looking for. So we know that we start by saying V is equals to IR. This is Ohm's law. But then because we're dealing with current sources, we express the resistance in terms of conductance. So that's going to give us I over G. And we then say, therefore, the current is going to give us G multiplied by V. So the current gives us the conductance times the voltage. And if we expand this, we can see that we've got three voltages. So it'll be three simultaneous equations with three unknowns. So we're going to say I1, I2, and I3 is going to give us the matrix G11, G12, G13, G21, G22, G23, G31, G32, and G33, all multiplied by the voltage we call V1, V2, and V3. And the voltage V1, V2, and V3 are the unknowns that we're looking for. So how do we find first the currents? So we consider each node and we say all the currents going into the node are positive and the currents going out of the node are negative. So in node 1, I1 will equal to the sum of the currents going in minus the sum of the currents going out. So 20 milliamps is going in, so this will be 20 and nothing is going out. So it will be 20 times 10 to the negative 3. I2, we have in node 2, we have only one current coming in, which is 5 milliamps, and nothing coming out. So we're going to have I2 equal to 5 milliamps, which is 5 times 10 to the negative 3. What about I3? In node 3, we have 10 milliamps going in and 5 milliamps going out. So this will be 10 times 10 to the negative 3 minus 5 times 10 to the negative 3, which then gives us 5 times 10 to the negative 3. Right, and that's our current matrix. Now in terms of the conductances G11, G22, and G33, we know that G11 is the sum of the conductances that are connected to node 1. Right, so G11 will be, you can see this resistor, that resistor, and that resistor are connected to node 1. So it would be 1 over 2 plus 1 over 2k plus 1 over 4k plus 1 over 1k. So that's going to give us 1 over 2k plus 1 over 4k plus 1 over 1k. So 1 over 2k, 1 over 4k, and 1 over 1k. And this gives us a value of 1.73 times 10 to the negative 3. G22, it will be the sum of the conductances connected to node 2, so that's 1 over 4k, 1 over 4k, and 1 over 2k. It's 1 over 4k plus 1 over 4k plus 1 over 2k. So that will give us 1 over 4, 1 over 4, 1 over 2, which gives us a value of 1 times 10 to the negative 3. And G33 will be the sum of all the conductances connected to node 3. And if we look at node 3, we have 1 over 4k, and we've got 1 over 1k. So that will be 1 over 4k plus 1 over 1k. And this gives us 1.25 times 10 to the negative 3. Right, and then the conductance G12, which is equals to G21, we know it must be negative, and it's going to be the sum of conductances connected between 1 and 2. So we can see that there's only 1 connected between 1 and 2, so it's going to be minus 1 over 4k. And this should give us a value of 0.25 times 10 to the negative 3. Right, and we know that's equal to 2,1. What about G23, which is equals to G32? This will be the sum of the conductances connected between 2 and 3. So 2 and 3 is also 1 over 4k. So we know that that's going to be minus 1 over 4k, which is negative 0.25 times 10 to the negative 3. Right, and the final one would be G31, which is the same as G13, will be the sum of conductances connected between 3 and 1, which will then be the 1 over 1k, negative in sign. And we will then have a value of 1 times 10 to the negative 3. Right, so we can see that all of the entries here are in milliamps. So what we can then do is we can then just say the final expression, which we know is going to be the current, is going to be 25 and 5. So we're going to say here 20, 5 and 5 is equals to the conductances, which were G11 is 1.73, G22 is 1, and G33 is 1.25, and then G12 is negative 0.25, and G21 is negative 0.25, and G23 is also negative 0.25, G32 is also negative 0.25, and G31 is 1, and that is also 1, but negative in sign. So this should be negative in sign here. Everything except the diagonal will be negative. Right, multiplied by V1, V2, and V3. Okay, and what we then will do here is we will plug these values in. So we are looking for the equation mode. Option 2, we're going to insert the coefficients. So that will be 1.73 minus 0.25 minus 1. And that adds to 20. The second one is negative 0.25. 1, again negative 0.25. And 5. And the last one is minus 1. And negative 0.25. And 1.25. And 5. Right, and if we solve this, it's going to give us the voltage values. So we calculate the value of the voltage, and the value of the voltage will give us 37.44. So V1 is going to give us 37.44, and then the value for V2 will give us 24.05. And the value for V3 will give us 38.76. Right, and finally, what units will this be in? Well, the units of the entries of the conductances were in milliamps. We didn't enter the value as times 10 to the negative 3, we just entered the values without the milli. Same happened with the current. So this expression then should be in millivolts. So that will be in millivolts and millivolts. Had we entered the actual expressions, what we would have found is that the actual value you get would have been 37.44 times 10 to the negative 3, and likewise for V2 and V3. So these are the values for the unknown voltages using analysis by inspection with the independent current sources. Thank you for watching this video and enjoy the course.